Welcome to the next segment or a sector in this course on basics of mechanical engineering under the heading of manufacturing. We have seen till now casting, metal forming, welding, and now we will try to see machining. Moment you say machining, that means to say there is some amount of material which is getting removed from the available material. If you look at casting and forming, they were constant volume process. That means to say starting and ending will be approximately the same volume will be there. When we went to welding, it was addition process, and in addition wherever it is required we added it. Now, when we move to subtracting process, we are going to remove material and then generate the shape, size, dimensions, whatever you want. Machining is a very important process. Wherever there is a non-symmetrical or wherever there is a huge amount of material to be removed, which cannot be changed, the shape change cannot happen through metal forming, we always go for machining operation. Now, next the basic logical question is, I have a material, now I have to remove material from the available material. So, then how do I do it? Should I use my hands or should I use a aid to remove the material? Now, the aid material is going to be the tool. So, now by using a tool, I am going to remove material and generate a shape. Simple example, you can try to think of carving out a shape from a given material, or you can see the people who work on making statues, right? Artisans who make statues, they use chisel and they use hammer. This hammer gives them impact load and the chisel is a sharp edge which helps in controlling the material removal. So, with that basic understanding, let us get into the topic of machining. The content of this particular segment of machining, we will try to have a small brief introduction, then we will try to understand history, then classifications in machining. So, there are different classifications. When you see that, it will be pretty interesting. Then you will try to see what is a tool geometry, because when we are trying to remove material from a stone or from a chunk, we have to remove the material in a controlled fashion. So, if we have to remove the material in a controlled fashion, then we will have to make sure the crack whatever gets generated or the shear whatever gets generated is according to the wish what we want. So, we will have to understand more of a single point tool. Then we will try to see a single point tool is not only a single point, it has multiple geometries attached with it. So, we will try to see tool designation, then we will try to see tool point geometry. When there is two material, tool material and the workpiece material, when it touches and moves, there is always a friction. This friction is going to lead to heat. So, then let us understand how heat gets dissipated, what is the influence of heat for removal of material. Then we will try to see chip formation. What is a chip? The material which is removed out of the chunk or the bulk material is called as chip. So, chip mechanism we will see, what are the different types of chips and a small recap on this machining. If you look at the video which is presented here, you will see here there is a tool. So, this is a tool. So, this which moves here back and forth, this is the tool. The tool is guided by a machine tool. So, machine tool tries to control what geometry or the profile the tool has to move. So, this is a tool and this is the machine tool. Now, you can see here this is the job or the workpiece. Now, on this workpiece you are trying to create a profile, a shape, a size, whatever dimension you want, you are trying to create such that it meets to your requirement. Now, this is done by rotating the workpiece. Why do you want to rotate the workpiece? Because you wanted to generate an axis symmetry profile. When you want to generate an axis symmetry profile, it is always a good idea to rotate the workpiece. The workpiece is held in a spindle. The spindle rotates and spindle holds the workpiece very strong. Now, there is a hard material which is called as a tool, which tries to have a relative motion against the workpiece to create a geometry you want. So, how is this motion given? Is by machine tool. So, machining is a metal removal process from the workpiece to get a finished good. So, here we try to talk about shape, size, dimension, if you want surface finish also. All these things are getting done. In a machining process, the either tool or the workpiece fed towards each other to remove the material in the form of a chip and the particles. So, what gets removed here? Flying. So, the flying part is nothing but the chip. Okay. Depending upon the depth whatever you give in digging, whatever you give, the chip profile changes or the chip thickness changes. If you go a small depth, you will try to get very small chips. When you try to go deeper, you will get large chips. So, the unwanted material which is removed from the workpiece is called as the chip. So, that is what is told here. The amount of material removed from the workpiece is limited to the finished quality of the final finished product. So, what is the depth you want? The depth of cut depends on many factors. What is the force you give from the machine tool? What is the relative motion you give? Against the workpiece, and the next one is how do you hold the workpiece? All these things matter. So, that is what we say, the amount of material removed. So, material removed will be for a given minute, what is the amount of material you take away from that. So, it can be the material removal rate. Moment I say rate, there has to be a time component. So, now I wanted to play safe. You can try to have what is the volume of material which is removed in a minute is called as material removal rate. So, the amount of material removal from the workpiece is limit the finished quality of the final finished product. Small amount of removal of the material better the surface finish and vice versa. But you should understand, once the material removal rate is very small or very less, the time for machining is going to be large. For example, if I want to remove 1 meter cube of volume in 10 minutes, in 1 minute, you see the time which is involved is reduced. So, the production can be very high. So, today what we do is we make stiffer or sturdy machine tool, and then we also try to improve the process parameter like rotating speed, the feed rate, the rate in which the tool advances. All these things are getting enhanced today. Very high speeds are there. Today the spindle speed, we talk about 1 lakh RPM. The feed rates, we talk about 500 millimeters per minute. It's very common nowadays, right? The machining operation are conventional, abrasive process and non-conventional process. They are classified as conventional. Conventional means where there is a tool used and the tool is harder and sharper than the workpiece. The immediate jump is non-conventional or non-traditional machining process, means here the tool need not be in contact with the workpiece. The tool need not be harder than the workpiece. So, those processes are called as non-conventional or non-traditional machining process. What is abrasive process? Here I know a tool and wherein which I dictate the tool geometry. In abrasive process, I make the tool into a small powder. So, the geometry cannot be dictated, but the tool will be always harder, the abrasive will be always harder than the workpiece. Again, there are exceptions. For example, when we try to remove a scratch from a glass, right. So, glass is a very hard material. So, here what we do is we try to use soft abrasives to remove the scratch. So, that is also possible, but there are exceptions. Generally, the manufacturing or the machining operation will be classified into three in machining. So, one is conventional process, two is non-conventional or non-traditional process, and the third one is abrasive process. So, whatever I have said, I have written it here. Material removal by sharp cutting tools is conventional process. Then abrasive process, where the material removal by hard abrasives, where the abrasives, the tool becomes an abrasive, the size is very small, geometry control is difficult. Non-traditional machining process, here the energy whatever you apply is different, they are not in contact, they do not touch, they are, the tool need not be harder than the workpiece. So, naturally what comes to your mind now will be, if I compare conventional and abrasive process, both are where the tool is harder, what will be the material removal rate? In abrasive process, since the tool size is very small and it will not be a single abrasive, multiple abrasives, the amount of material removed will be very small or very less as compared to that of conventional. Any look into history, machining has been quite some time existing. Whenever they wanted to make some design on wood, they have been using machining operation. When they wanted to drill a hole on a wood, they have been using machining operation. So, the machine structure was different, it got evolved. So, here they have used impact load, then they have used the control movement of the tool such that they can generate the profile. They started with wood and slowly they got the expertise and they got carving it on the metal also. Right. Exhaustive operations have been done by the artisans. In the past, they who were working in the king's regime or in the kingdom or in the courtyard of the king, where they wanted to make artilleries as well as artifacts. The root of machining can be traced back to ancient civilization. The Egyptian, Greek and the Romans developed various tools and techniques for shaping stone, wood and metal. Metal forming was also done, stamping was also done. They also did parallelly machining operation. And if you look at the artisans who are making statues, they used to carve stones with a tool which is harder. They use a chisel which is harder than the material stone, and then they start carving it in a very controlled fashion. So, these early craftsmen used handheld tools like chisel, saw, file to shape material with precision and skill. So, in the ancient era, if you go through any of the museums, you can see lot of dies made out of elephant tusk. So, where they do lot of small features, fragile features, they were all made through precision tools. They carved, they use files to make it. This has been there. The lathe, one of the oldest and the most fundamental machine tool, was invented in ancient Egypt in 1300 BCE. The ancient Egyptian developed a simple lathe known as Egyptian bow lathe. So, this is a bow and this is a lathe machine. Then subsequently, when industrial revolution started in 18th century, a lot of things started developing much faster, and of course, World War I, II were there. So, it demanded lot of war front devices, piston and other things. So, industrial revolution in the 18th century marked the significant milestone of machining history. The development of machine tool such as lathe, milling machines revolutionized the manufacturing process. These machines introduced mechanization. So, when as a mechanical engineer, you will try to read lot of mechanisms, 3-bar mechanism, 4-bar mechanism. All these mechanisms were given an aid for the machine tool development. So, they used to give a drive at one place and they used to have a mechanism which used to transmit the drive or the feed, whatever it is, to the tool. So, these machines introduced mechanization and automation, greatly increased the productivity and precision. James Nasmyth, a Scottish engineer, is often credited with the development of the first true milling machine around 1829. The design incorporated a rotary cutting tool and a table that moved in multiple directions to achieve precision and versatility. So, in lathe machine, what we saw a video is the workpiece was rotating. When this gentleman, James, what he did is, he developed a milling machine wherein which he made the tool to rotate and he made the workpiece constant. Constant means it can move at a required feed rate. So, in lathe machine, tool was given the feed rate. In milling machine, again the tool was given, but the tool was rotated. In the late 19th century, precision machining techniques gained prominence. So, they started making Swiss watch, very small, mechanical activated watches, mechanical activated systems wherein which they use spring to store energy. Springs were machined. You could have done it by metal forming, but springs were also machined when very small precision are required, because the spring back in metal forming was always dominating. The introduction of grinding machine played a significant role in the industrialization process of precision machining. So, what was then, what then the next stage you can see, and today you can see. Today it has gone much far, but today you can see machines like this. So, here still the drive was given by hand, here the motorized drive started coming into existence. Today you have very high precision machines with multiple axes in control. Now, let us get into the classification of machining. So, material removal process are classified into conventional, abrasive process and non-traditional machining process, or it is also called as non-conventional machining process. It is all the same, conventional, non-conventional. So, how are they classified? They are classified as single point cutting and multiple point cutting. In single point cutting, we used to have a tool. The tool will have a single tip. So, that tip will come in contact with the workpiece and start machining. And here the workpiece was rotating, it was held in a lathe machine. Majority of the time, axis symmetry parts can be done in this machining process. Next comes drilling. In turning, we had a single point, in drilling, we had 2 points. So, drilling operation is always used to make a hole. The relative motion is given between the tool and the workpiece. Here, the tool rotates. When you want to drill a hole, the tool rotates, right? The tool rotates and it advances step by step towards the workpiece and it sinks into the workpiece, makes a hole. So, here the drill had to be made 2 point. Why? Because when the material is removed, it as and when you go deeper and deeper and deeper, the material which is removed has to be brought out in a simpler fashion. So, when we have to bring the tool material out, so they used to have a flute. So, there will be a flute through which the chip flows out and the material is removed and you drill a hole. What is milling? Milling is you can have more than two. You can have more than two cutting points. So, and they can be used to remove material in a much faster fashion. So, instead of two what was there, now I will have a tool where in which there will be multiple cutting edges. Each of the cutting edge will try to remove material. So, I can remove lot of material. If I want to make a flat plate or a stepped slot, then I use milling operation. Other machining operations are a combination of turning. You can have boring, you can have, then you can have many other small things, which is a combination of turning, drilling and milling also you can have. Combination or other special type machining process you can have. When I get into abrasive, then in abrasive there are two types. One is called as loose abrasive, the other one is called as fixed abrasive. That means to say the abrasive can be fixed at a certain point and that can be used as a tool for machining. Loose abrasives are where there are abrasives spread on top of a surface and it can do. For example, if there is a mud which is spread on top of a flat tile, right, and when you walk, there is a friction between your shoe, the sand particle and the tile, right. Now, based on your load and the action whatever you do, there is a scratch which is getting created. If many scratches are formed on the tile, the material is removed. So, loose abrasives work in the same phenomena. Here the abrasive size is very small. We talk in terms of microns. So, it can be somewhere between 10 microns to 100 microns. That will be the size of the abrasive. The abrasive can be of multiple material, hardness material. Those loose abrasives are used, they are spread on top of a workpiece. You have a load which is applied on top and then you try to remove. In fixed, there is a abrasive. These abrasives are bonded together by adding a binder to it. So, every abrasive has a fixed location. So, when that point particular abrasive comes in contact with the workpiece, it removes and then it waits for the next round to come. So, generally what we do is the fixed abrasives are fixed on top of a wheel. So, this wheel is called as grinding wheel. So, this is the process which is called as grinding operation. So, suppose you assume there is an abrasive sitting here. When it rotates, this abrasive comes in contact, removes material and it will wait for the next time on the rotation to come and remove material. So, those things are called as fixed abrasives. So, we have discussed that. Then when we get into non-conventional or non-traditional machining process, we use mechanical energy. So, mechanical energy is we try to use high jet of water, okay, where the potential energy is converted into kinetic energy and this kinetic energy tries to remove material. In the jet of water, I also add loose abrasives. So, I remove material. So, those operations are called as mechanical energy process. The other one is I use electrochemical. I make positive electrode, negative or positive workpiece, negative electrode and I apply current. Along with it, I also have some amount of media which is an electrolyte through which there is an etching operation happening and I remove material. This is accelerated etching. So, along the seashore you can see material getting eroded in the presence of salt. So, here I use electricity and then I accelerate it. Thermal is I use heat, laser, I use laser to heat the material and try to remove the material. So, then there is without applying electricity, I only use chemical to remove material. So, what do? I try to keep the substrate, then I try to keep a mask on top of it. In the mask, I try to remove material and then I try to do etching. Many of the artists, what they do is they try to do chemical etching. If they want to create a photo of your legend, whoever it is, a sportsman. So, what they do is they take a thin copper sheet or a brass sheet and then they put the mask, they etch it. And then they try to create it and this can be used as very good artifacts. So, these are the classifications of machining processes or material removal processes. Cutting tool geometry, single point. Since the next couple of slides are very important to be focused only on the slides, we will give more priority or preferences only to the slides. I would request all of you to focus on the slides. Now that you know, what we have is a tool which is a cuboidal tool. A cuboidal tool. This cuboidal tool, we know the property of the tool is it has to be harder than the workpiece. And you also know that if I have a line contact, I will have to apply lot of force. Basically, pressure is nothing but force per unit area. So, now I have to reduce the pressure. If I have to reduce the pressure, I have to convert this line contact into a point contact. I have to convert this line contact into a point contact. So, if I have to convert this into a point contact, then I have to do modifications on the face. So, I have to do change in this face, on the top face, and then also in the side face. So, I will try to say on the top face I have to make a change, on the side face I have to make a change, and in the front face I have to make a change. Why? When I make all these things, I would convert it into a single point. Now, when the workpiece is in contact with the tool, it is going to create chip. Now, the chip whatever is there has to flow through the rake face or has to flow through the face of the tool. So, when it has to flow through the face, I have to make sure that I give an angle such that the chip can easily flow on the face and get out. So, I will now try to focus on the angles. So, if you see the side view of the tool, you can see there is a rake face. The rake face is a face where the chip moves, and here we have said back rake face. So, just hold on for a minute. When we go through the other views, you will understand what does this back come from. So, there is a rake face. In this rake face, the chip will move out. The other face is when the tool is moving towards the workpiece, there will be now on the top chip moves. Now, there should be a clearance which is there or a relief which is there such that this face of the tool will not come in contact with the workpiece. So, that angle is called as relief angle. The angle which is in between the relief angle and the rake angle is called as the lip angle. Okay. So, back rake and end rake. So, now we will try to see what is this back and end. From the side view, let us go to this view. In this view, you are trying to keep the tool in and see from the top. This is a top. When we see from the top, you see here there is a shank, and then you see there is a cutting edge and there is a end cutting edge. This cutting edge will be in contact with the workpiece as and when the feed rate is moving. So, between the shank and the tip, now the tip is converted into a nose radius, because a tip which is there over a period of time gets blunt. So, I am making a radius so that I have a larger area through which the tool is coming in contact with the workpiece. So, you have a nose radius and then you have a cutting edge. You have a cutting edge which comes in contact with the workpiece, and you have a nose radius where the point is converted into a nose. So, there you will have a radius. The other end of this, because when you see here, this is the cutting edge, this is the cutting edge, and now this edge is also there. So, that edge will try to form an angle which is called as end cutting edge angle. this portion, right. So, this portion will also have an angle. Now, this portion will also have an angle, this portion will also have an angle. So, now you see these, there are 3 angles. Now, let us try to see the side view of this. So, in the side view, you try to see the side cutting rake angle. The plane whatever is there is never perpendicular, it is inclined at an angle. This plane is inclined at an angle, right. So, you will have a side rake angle, and then in the relief whatever we saw here, we will have a side relief angle. So, when we try to note down, please see, this is side end relief and this is side relief, right. And here you see a back rake angle and you see a side rake angle, back rake and side rake. So, these are 2 different rake angles, right, back rake angle and side rake angle. Now, what is left? You have already seen the nose radius. So, now what is pending is the clearance angle. So, end clearance angle and side cutting angle also you saw. So, it is only end clearance angle. So, end clearance angle is, it is not a straight line what we get, it is after a certain point we also try to maintain an angle. So, this is called as the end clearance angle. This is called the end clearance angle. So, we have end cutting edge angle, then we have end clearance angle, side relief angle, end relief angle, back rake angle and side rake angle. So, if you see there are 6 angles and there is 1 nose radius to define a tool, a single point cutting tool. So, if you see a single point cutting tool, these were all 2-dimensional, where in which we had orthogonal projections. If you see a tool looks like this. So, this will give you more clarity, this figure will give you more clarity. So, you see here is a shank, right. From a shank which is cuboidal, you have to cut this angles to the tool. This is straightforward nose radius. Now, when this is the cutting edge, this is the cutting edge. The angle towards this is the back rake angle through which the chip moves. Then we have a side relief. So, here if you see from here to here, whatever is called as the side relief angle. And when we try to, a cuboid is given an angle, then it is called as side cutting edge angle. Then we have, this is end cutting edge angle and this is side rake angle. So, these are the 6 angles with the nose radius for a single point cutting tool. So, I have explained about it. Shank is used for holding the tool. The face, it is the surface on which the chip impinges, the rake face, chip impinges and flows along with it. Flank face, the flank are 2 surfaces of the tool facing the work. They are called the side or the main flank and the end or auxiliary flank. The cutting edge, they are the intersection of the flank face, the face and the flank. They are called as the side and main cutting edge. Main cutting edge and the end cutting edge angle. So, they are all the side cutting edge angle. So, the last one is the nose radius. So, shank, face, flank, cutting edge and nose radius, these are the angles which are generally used for a single point cutting tool. A single point cutting tool designation, there are 3 major things which generally people talk about. They are ASA system, ORS system and NRS system. There are 3 different types of system, because every country had their own convention and then they did. We will try to focus only on NRS, so that you will try to understand how the NRS angles are derived. Then parallel analogy you can do for ASA and ORS. And this will also give you a clear example of your understanding in the engineering drawing, what we studied in the first year, where you cut a section, you rotate it and then you try to find out the angles in it. So, NRS system, so the tool whatever you have is cuboidal. From there you are supposed to make 6 angles and 1 nose radius. So, if that is the case, you have to have references. So, the NRS system will have 3 reference planes. With these 3 reference planes, you try to figure out the angle deviation from these planes, and then you try to figure out the end cutting, side cutting, edge cutting, all the angles. So, in the NRS system utilizes 3 phases, all the 3, ASA and ORS also uses the same. The only thing is, what is the angle between the planes matters. So, based on that, then we try to keep the tool as reference and then we try to understand. So, normal rake system utilizes 3 planes as reference for measuring various tool angles. These 3 planes are listed below. One is reference plane pi r, the other one is cutting plane pi c, and the third one is a normal plane pi n. What is pi r? Pi r is the plane perpendicular to the cutting velocity vector. With cutting velocity vector is Vc, we will see in the figure in the next slide. The cutting plane, it is a plane perpendicular to reference plane. So, reference plane and it is perpendicular. So, this is plane and perpendicular. So, cutting plane, it is a plane perpendicular to the reference plane and contains the principal cutting edge of the tool. It contains the principal cutting edge of the tool. So, now what we are trying to do is, first we said everything is perpendicular. Now, we try to maintain the perpendicularity, but try to have a small angle. So, that matches with the principal cutting edge. The next one is the normal plane. It is a plane perpendicular to the principal cutting edge of the tool. The normal plane may not be perpendicular to the reference plane. So, reference plane and cutting plane are perpendicular. The normal plane need not be perpendicular to the reference plane, but it is perpendicular to the reference plane. However, the normal plane is always perpendicular to the principal cutting edge. So, first we saw reference plane, then we saw cutting plane, then we saw normal plane. So, pi r and pi c, right, and then pi c and pi n. So, pi c is perpendicular to pi r and contains principal cutting edge. NR is perpendicular to the principal cutting edge. Unlike ASA and ORS system of tool designation, where all 3 planes of reference are mutually perpendicular in NRS system, right, all perpendicular. In NRS system, the 3 planes of reference may not be mutually perpendicular. In ASA and ORS, they are perpendicular to each other. So, they will become mutually perpendicular only when the cutting tool has 0 inclination, then in that case NRS system and ORS system will be the same. So, this point is only to make sure that how can you transfer from here to here, here to here, ASA to ORS, ORS to NRS, you can transfer it. All the 3 reference systems are followed, and when we try to buy a tool, we should try to ask them, does it follow ASA system, ORS system or NRS system. Now, this is the plane which we are talking about. So, there are 3 reference planes. One is pi c, which you can see along the cutting plane. The other one is pi r reference plane, and the next one is pi n, which is normal to it. If you can see both the figures, like this is one plane, this is the other plane, and this is the third plane which is at an angle. So, now when we try to take a tool and we try to section the tool. So, let us try to take section AA. So, this is AA, right. So, when we try to section AA and we try to project it, you try to see here alpha O and gamma O is present. Now, we try to incline at an angle and then we try to cut it. So, that is BB. We try to project BB, we try to get alpha n and gamma n. Okay. So, now you can see there are 3 planes. Where are the 3 planes? You can see here there is a orthogonal plane gamma O. So, this is orthogonal reference. So, you try to take a section along it. which is represented as BB. So, when we try to cut and then project the section, you get a BB section here, where in which we can get two angles, the alpha n and gamma n. Then when we try to take a section which is normal reference gamma n, which is a normal reference plane, we try to take a section AA. When we try to project it, it comes as, you try to get alpha O and gamma O. Okay. These are the two things. One is alpha n, gamma n, then alpha O, gamma O, right. And then you try to have an inclined angle lambda, which is nothing but the angle between the orthogonal and the normal is lambda, and along the cutting edge what you have is the reference plane pi r. So, now you can see pi n, pi r, pi o is there, and then this pi r, when we try to draw it, you can try to see the other angles will be seen. Now, various features displayed in NRS system of tool designation. Similar to ORS system, NRS tool designation also signifies two different rake angles, two different clearance angles, two different cutting angles and one nose radius. So, that is how it is. You will have angle, that is rake will be 2, then you will have clearance will be 2, then you will have cutting will be 2, and then you will try to have your nose radius, that will be 1. The various features of single point cutting tool that NRS system specifies are normal rake angle, you have an inclination angle lambda, then you have a normal clearance angle alpha n. So, normal rake angle will be, it is the angle of orientation of tool's rake surface from reference plane and measured on a normal plane. Please go back to this both the figures, and where in which there is a plane and a axis, please understand that, then only you can interpret this. The normal rake angle gamma n, it is the angle oriented of the tool rake surface from the reference plane pi r, where is pi r? Pi r is here, right, pi r, and measured on the normal plane pi n. Where is pi n? Pi n is the normal plane which you can see here. Pi r is the reference plane, pi n normal plane. So, that is called as gamma n. What is inclination angle? It is the angle of inclination of tool principal cutting edge from the reference plane pi r measured on the cutting plane pi c is the inclination angle. So, this is the angle which is given here, z orthogonal and z normal, the angle inclined is lambda. Normal clearance angle which is seen in this plane, you can see that is an angle of orientation of the tool's principal flank surface from the cutting plane to measured on the normal plane. The auxiliary normal clearance angle, it is the angle orientation of the tool's auxiliary flank surface from the auxiliary cutting plane measured on the auxiliary normal plane is gamma n prime. So, the principal cutting angle is phi, and this will be phi 1. So, which again we can see from here, phi and phi 1. So, the principal cutting edge angle is phi, it is the angle between the cutting plane which contains the principal cutting edge and the longitudinal feed direction measured on the reference plane. The auxiliary cutting edge will be phi 1 and the nose radius is r. Thank you very much.